Hey everyone, and welcome. Today, we're going to crack the code on a huge part of calculus, the indefinite integral. You know how you can find a rate of change? Well, have you ever thought, can I go backwards? If so, you are in exactly the right spot. Let's jump in. So, this is the big question, right? Given a function's slope, can we figure out the original function? It's kind of like a detective story. We have the clue, the slope, the derivative, and our job is to trace it back to find the source. All right, so here's the game plan for today. First, we'll talk about this whole reverse problem idea. Then, I'll introduce you to our secret weapon, the integral. After that, we'll solve the big mystery of the plus c. Then, we'll get practical and find a specific curve. And finally, we'll level up with some trickier problems. Okay, let's kick things off with section 1, the reverse problem. So you've probably spent a lot of time learning how to find a slope from a curve. Now, we're just going to flip that completely on its head. Right. So you're used to this. Start with something like x squared, find its derivative, boom, 2x. Easy enough. But what if we do the opposite? What if we start with the slope, 2x, and ask ourselves, where in the world did this come from? That's the game we're playing today. Now, to solve this kind of reverse problem, you can't just guess. You need a tool, a specific mathematical operation. And that, my friends, is the integral. And here it is. This funky-looking long S symbol, that's the integral sign. The f of x is just the function you're working with, and the dx at the end just tells you, hey, we're doing this with respect to x. The whole shebang is called the indefinite integral. And really, all it's asking is, what's the function whose derivative is this thing inside? It's also called the antiderivative, which makes a ton of sense, right? I love this slide because it shows the two processes side by side. Going forward, differentiating x squared gives you 2x. Going backward, integrating 2x gets you back to x squared. But wait, see that plus c? That little guy is super important, and honestly, it trips a lot of people up. So let's figure out what it's all about. And that brings us right to our next section, the mystery of plus c. I mean, why isn't there just one answer? Why this extra piece tacked on at the end? Let's investigate. Okay, let's get right to it. Seriously, this is probably the #1 question students ask. But why do we have to add plus c? Don't worry, there's a really good logical reason for it. So check this out. What's the derivative of x squared plus 5? It's 2x. Okay. Now what's the derivative of x squared minus 10? Also 2x. The derivative of x squared plus a billion? Still 2x. Why? Because when you take the derivative of any constant number, it just becomes 0. It disappears. So here's the big takeaway. The process of differentiation basically destroys any constant that was attached to the function. It's like it erases part of the evidence. So when we integrate, when we go backwards, we have no way of knowing what that original constant was. Was it 5? Was it -10? Was it 0? We don't know. So the derivative 2x isn't the child of just one function. It comes from a whole family of curves. And plus c is our brilliant, simple way of saying, hey, it could be any of these constants. It's the general solution that covers all the bases. But you know, a family of curves isn't always good enough. Sometimes you need the answer, the one specific function. So how do we do that? Well, that's what section 4 is all about. We're going to use something called an initial value problem to pin it down. All right, here's a classic example. We're told the derivative is 2x minus 1. But, and this is the important part, we're also given a clue. We know our original function passes through the point 0, 3. That little piece of info, that's the key that unlocks everything. This whole setup has a name. It's an initial value problem. You've got the derivative, and you've got one point on the graph, an initial condition. And your mission, should you choose to accept it, is to use that point to sift through that infinite family of functions and pull out the one single correct one. And the good news is, there's a super straightforward 3-step method to solve it. Step 1, you integrate like normal to get that general solution with the plus c. Step 2, you take that point you were given and plug it in to figure out exactly what c is. And finally, step 3, you just rewrite the function with your newfound value of c. That's it. And here we see it happen in real time. First, we integrate 2x minus 1 and we get x squared minus x plus c. That's our general solution. Next, we use our clue, the point 0, 3. We plug in 0 for x and 3 for f of x. So 3 equals 0 squared minus 0 plus c. Well, that makes it pretty darn easy. C is just 3. For our last step, we just pop that 3 back into our general solution, and there it is. Our specific function is x squared minus x plus 3. Mission accomplished. All right, you've got the main idea down solid. So for our last section, let's level up a bit. We're going to tackle some examples with trig and exponential functions to really sharpen those skills. Okay, example A. Let's evaluate the integral of 6x squared minus secant squared x. Now, don't let it intimidate you. We can just take it piece by piece. First, what gives us a derivative of 6x squared? And second, what gives us a derivative of secant squared? So for that 6x squared part, we just reverse the power rule, which gives us 2x cubed. Now for the secant squared part, you gotta reach back in your memory for those trig derivatives. Remember that the derivative of tan x is secant squared x? So the integral of secant squared is just tan x. We put it all together, remember our minus sign, and tack on the plus c at the end. Final answer, 2x cubed minus tan x plus c. All right, last one, let's do this. Example B. Find the integral of e to the x plus cosine x. Again, it's all about pattern recognition. What functions have these as their derivatives? This one's my favorite. It's almost a trick question. The integral of e to the x is, well, it's just e to the x. And what function gives us cosine when we differentiate it? That's right, sine. So the answer is just e to the x plus sine of x, and don't you dare forget our buddy, plus c. Okay, let's wrap this up with the key takeaways. Number 1, integration is just differentiation in reverse. Simple as that. Number 2, that plus c isn't just some random thing to add on. It represents a whole family of functions that all have the same slope. And number 3, if you get a little clue, an initial condition, you can nail down that c and find the one specific function you're after. So we've pretty much cracked the code on how to go from a slope back to the original function. But what if I told you that wasn't the only thing the integral could do? What if the same tool could tell us about the area trapped underneath the curve? Chew on that for a second. That question is the bridge from what we did today, indefinite integrals, to the next huge topic, definite integrals. And trust me, that's where things get really interesting.